Hello everyone, good day. So today we will discuss on Anova, analysis of variance. This is one of the most powerful hypothesis testing available for continuous data. Let's get into the details of it and get to learn more about it. Okay. As you see on the screen, Anova, right? When to use it? That's an important question. Everybody should be very clear in terms of when to use an Anova. Right, so Anova analysis of variance is a parametric test, right, used to test the means of a variable which has more than two levels, right? So let's take an example of a variable as speed of a car, right? And the variable speed of the car has, say, 6 levels in it. For example, the number of gears, right? So first gear you will have a different speed, second gear you will have a different speed, third gear you will have a different speed, fourth you will have a different speed, fifth you will have a different speed. So 6 levels of data, sixth gear you will have a different speed. So you have 6 levels of that data in variable speed of the car. This is exactly where we will go ahead and use Anova, right? Where you have a single variable and you have multiple levels in that variable, right? So that's when you have 2 levels, you will go ahead and use 2T test, right? So when there are more than 2 levels is where you will need to use analysis of variance, wherein 2T test cannot be put in use. Okay. So that's where and when to use Anova. What are the pre-model conditions and steps followed in Anova, right? As I mentioned before in our previous statement, it's a parametric test. So the first condition is that it should be continuous data. Y should be continuous in nature, right? Exactly, and that's what you see here, and that's a step 1. So you need to validate for yourself whether it's a continuous data or not. And second condition is that Y should be normally distributed, and that's technically the step 2 in conducting an Anova, right? You have to understand whether the data given to you is following a normal distribution or not. That's step number 2. And what's condition 3? All levels in Y should have or must have equal variance, and it's a mandatory step, and we will discuss more in detail about this step. This is a very, very important condition to be met before we put Anova in use. Okay, and that's step 3 for you, right? And step 4 is just run the Anova in Minitab or Excel and get your results, right? So 4 steps typically. 1 is to validate for yourself whether it's a continuous data. Second, check the normality. Third, check for equal variance. And fourth, run the Anova, right? So once you run the Anova, you obviously will get the results. And there are a few things which you will need to validate even after that exercise, right? For you to use Anova very successfully, those are the 3 conditions you will need to check even after Anova. 1 condition is residuals must be normally distributed. Once you run the Anova, you will get residuals, and those residuals must be normally distributed. And residuals must be random. It should not be correlated with each other. So if I am plotting it over time, there should not be a correlation between these residuals. It should be randomly distributed, and it should be independent with each other. And residuals must contain mean as 0. Right? So these are the 3 conditions, post-model conditions. We will discuss about this when we are doing the exercise. Okay, so we discussed on the steps to do Anova, preconditions and postconditions. And now let's understand where we apply Anova. Right? Anova, as I told you, is a hypothesis testing of means. When we are interested in testing the statistical significance of an X, which is an independent variable, on Y, which is a dependent variable, right? So if you want to really test the statistical significance of X on Y, or in other words, does X have an influence in causing changes in Y or not? If you are interested in this, and if you are basically fulfilling all the conditions what we have, the pre-model conditions what we just discussed, that's when you will go ahead and apply Anova, right? So another important concept in any of the hypothesis testing is that you're testing your hypothesis. That means you have certain assumptions, you have certain belief, right? This is what you call as hypothesis. Unless proven otherwise, that will stay true. And that's in our normal lives as well, right? We believe in certain things unless and until it is proven otherwise, right? So what you believe in, right, is typically null hypothesis, right? I don't see any change in anything. Everything is the same. Things are equal, right? Nothing is related to each other. So this is the null hypothesis. This is the by default assumption I have. And what is to be proven to change my belief is typically the alternate hypothesis. It means things are not equal. They are different. They are related, right? So it's the opposite of your null hypothesis, which you want to prove, right? Null hypothesis is your belief, and alternate hypothesis is something what you want to gather evidence and prove so that you can project your null hypothesis and go with the thing what you have just proven. Okay, so null hypothesis generally represented as H naught, right? So that means mean of the first level is equal to the mean of second level is equal to the mean of third level, and how many ever levels you have in that variable. So we assume that means are equal, and that's null hypothesis for you. An alternate is something what you believe that at least one of this level, HA is what we use to denote it, at least one of the mean are not equal with the others, right? At least one. So I would even write it mu1 not equal to mu2, not equal to mu2, mu3 not equal to mu n, right? So at least one. I don't need a scenario where everything is different. At least one is different from the rest of it. Well, that becomes your alternate hypothesis. Okay, so that's the basics of Anova before we get started. Okay, and before I show you an example, I just want to give you certain terms which you really need to be familiar with, because this is something what you will see in the Anova results, and these terms are really important for you to take a decision as well. First and the foremost, you get to see something called as degree of freedom, right? And this is a very important and a simple concept which is extensively used in statistics, and whenever it comes to analyzing data statistically, degrees of freedom comes in really important. So it's a very simple term. If I have to give you a plain example, it's like currency, right? The more you have, the more will be your spending power, right? You can spend more, right? So when it comes to data again, right? When you have more data points, is where you will have a powerful exercise on analyzing that data done. So you will be able to extract more information, accurate information, provided you have more number of data points. So degree of freedom is something which we need as high as possible for us to conduct the analysis efficiently and get more information out of it, right? So generally we use the formula n-1, right? I can use a simple example and try to prove you that. So let's say you have got $500 is the budget which you need to expend. You need to spend, right? And then you are sure and certain that you want to buy 5 things, right? You want to buy 5 things, and 500 rupees is your budget, and you want to completely exhaust it. You don't want to save it because it gets lapsed tomorrow. So as a person, you have to buy 5 things. So the first 4 things what you buy can be of any cost. can be of any price. Although you know that your total budget is 500, I can buy the first stuff for 20 rupees, 30 rupees, 400 rupees, 200 rupees, whatever, right? And the second also, I can have kind of a liberty, I have a freedom to choose my price, but obviously it has to be within the budget. Third one also, I have some range available, right? Fourth product also, I have some range available. But once you exhaust all the four, you have only one product left, and that you cannot choose arbitrarily because you have a fixed number. You've already spent 500 rupees or less than that on your four products, right? So the fifth product you cannot buy as per your choice. You can only buy for a specific price because I've already spent. Say for instance, you would have already purchased things for 450 rupees for four products, and the fifth product is no more your choice because you can only buy a product which is costing 50 rupees, right? So your freedom is getting stopped there, or your freedom is getting exhausted there, right? So your degrees of freedom is only on four products, and the fifth product you don't have any freedom. So you had five products, so n minus 1, 4 is the degree of freedom where you can exercise it, and the fifth one you don't have the freedom. So this is technically the concept, right, of degrees of freedom. I hope you understood the concept. In case if you have got any specific doubt, please do write to me. I will try and give you more explanations and examples to get you very, very comfortable in this topic, okay? And the next set of things what you really need to be very aware of are the variations, different types of variations, right? You get to see within variation, between variation, and total variation, right? So within variation is something what you call as a variable we just took as speed of the car, and we know that there are 6 levels, 6 gears in it, right? So within variation, within each gear, first gear, I have got say 10 data points. So out of that 10 data points, how is my variation? So that becomes within variation for me. So what is between variation? So between first gear and second gear and third gear and fourth gear, right? So how are the variations happening between levels? So that becomes my between variation, right? And then obviously when you add these two things together, that's when you will get the total variation, right? So between variation is also called as a model variation, and within variation is technically called as an error. So when you get to see these terms in Minitab, you may see that between variation mentioned as model and within variation mentioned as error, right? And for each of these variation, you will have a degree of freedom associated with that, right? How many degrees of freedom we could exercise to come up with this particular number? How many degrees of freedom we could exercise to come up with this particular number? That is going along with each variation listed down here. So for each variation, there will be a degrees of freedom attached to it. Okay. So the third concept is sum of squares, which I really don't need to explain to you because when you have learned about standard deviation, that's the first step what we did, right? When you want to calculate standard deviation, you calculate the mean first, and then you take the individual differences of each data point from the mean. So you will get to see that there are certain negative values and positive values. So to avoid the cancellation effect, we go ahead and square it, right? And that squared value is called as the sum of squares, right? And then if you want to calculate the variance out of it, we just went ahead and divided it by n minus 1, right? And that n minus 1 is nothing but your degrees of freedom. So you divided your sum of squares with degrees of freedom, and then you got the variance. So if you want to calculate standard deviation, you just need to take the square root of this variance, right? Then you will get the standard deviation. Okay. So those are the important factors which you will need to keep in your mind when you are doing Anova. And the remaining three are very, very important. These are the decision makers, right? So once you run the analysis of variance, you will see a value called as an F value coming alongside your Anova results. So F value is nothing but the ratio of between variation to within variation, right? So if I have to take the ratio of between to within, I'll get a particular ratio which is called as the F value, right? And this is a very important measure, right? So technically it is basically the variance is what I will calculate, and it is the variance, the ratio of the variance between to within will give me the F value. And this F value is compared with the standard F distribution value, right? So which is called as the F critical value. So once I calculate my F value by taking the ratio between to within variation, I record that value, then I go ahead and check in the F standard distribution with the degrees of freedom associated with between and within. I will go ahead and see what is the value listed in that F distribution table. So I've got two values in hand. So F value, which I've already calculated with my analysis of variance, and for a particular confidence interval and for a particular degrees of freedom from the F distribution table, I have got an F critical value. Now the point of contention is that, right, you have a hypothesis to be validated, right, and you are ready to take certain risk in that hypothesis, because before we get started we always set the confidence level, right? So we will generally set it at 95%. So 5% is the risk what I'm ready to take to forego my null hypothesis, right? So if I have certain beliefs, right, I'm ready to take a risk of 5% to forego that belief and to believe the alternate hypothesis, right? So technically what you're going to look at in the F critical table or in the F distribution is that what is the percentage or what is the probability that the F value is higher than the F critical value. So when the F value is higher than the F critical value, so when a standard distribution contains 100% of the data, right, and F critical value comes there, and if the F critical value is at 95%, right, so if it is the F value is more than F critical value, obviously it is in the 5% range, because 95% of the data set will be on the left side of my F distribution, right, with the F critical value. So F value, if it is more than F critical value, that means it is going into the 5% zone, right? So 5% or less than that, where I'm comfortable in taking that risk. So if the F value is more than the F critical value, that means I'm taking less than 5% risk in rejecting my null hypothesis, right? So P value is a probability value which will be thrown out by Minitab again. If it is less than 5% is where you will go ahead and reject your null hypothesis. So these are the few basic terms which you should be very well aware before conducting the analysis of variance. I hope that you're clear with the basics. Again, do not worry. In case if you've got any questions, please drop an email. I will try and answer your queries as soon as possible. Now that we have learned the basics, let's see in real life how do we solve an Anova, solve for analysis of variance, right? If we have to conduct a hypothesis testing, how would you go ahead and do it, right? So let's see that in this question, let's assume that there are three prototype of aircraft engines developed by a company, right? Prototype A, prototype B, and prototype C. These are the three different engines what they have developed, and the engineers have tried taking some sample data on the flight range in nautical miles for each of these prototypes, right? They have fueled the engine, they have just taken it for a ride, and then they have recorded how many nautical miles they could cover with the fuel filled for prototype A, B, and C, and they have got altogether 30 samples, 10 samples for each prototype, right? So the engineer wants to check whether prototype A is equal to prototype B is equal to prototype C or not, right? And the alternate, at least one mean is different from the remaining prototype. So null hypothesis is that mean nautical miles covered by prototype A is equal to mean nautical miles covered by prototype B is equal to mean nautical miles covered by prototype C. Alternate hypothesis will become at least one of the means are different. Okay, so here what you will need to do. Okay, so this is how the null hypothesis and the alternate hypothesis will look like, right? H naught is equal to mean of prototype A is equal to mean of prototype B is equal to mean of prototype C, right? And alternate hypothesis will become at least one of the means are not equal. At least mu A not equal to mu B, or mu B not equal to mu C, or mu A not equal to mu C. At least that is what you want to prove, right? So that becomes the alternate hypothesis for it. Okay, so how do we do this, right? We have two options to conduct this. Either we can use Minitab or we can do it in Excel, right? So easier way to look at it is Minitab. So let me open Minitab for you, right? So in here, when it comes to Minitab, right, there are a few things what you will need to understand, right? The commands are very simple. It's all pre-fed. You don't really need to write any codes there, right? So all you need to do is to stick the data, copy paste the data to Minitab, right? And then you go to stat. What you see here, you go to stat, right? And then I shall guide you to basic statistics and then normality test. This is the first test what you need to do, right? So I repeat, go to stats, basic statistics and normality test. So you will get a window like this, right? Let's look at that window. Hang on a minute. I'm going to show you that window. Okay, there you go. This is the window we're talking about. So you may have got this window, right? So what you need to select, right? So you have got variables here, and then the type of normality test what you want to do, right? So what I would do is that I will go back and I will select the first level, right? Prototype A. I'm not interested in anything. I'm just interested in doing the Anderson-Darling test, right? And then I will click OK. So I'm going to get this result, right? Let me show you the result what I get in Minitab. Yes. So I got this result. What you saw here, that's the Anderson-Darling normality test. So look at the p-value, right? P-value is 0.523, which is more than 0.05. So it is 52%, right? What was the null hypothesis in my normal distribution test? This is also a hypothesis testing. So my null hypothesis was that it is a normal distribution. Everything is normal, right? It's a normal distribution. And alternate is it is a non-normal distribution. So can I reject my null hypothesis? No, because I'm taking 52% risk if I reject my null hypothesis. So I will go with my null hypothesis saying that prototype A, the samples what I've collected is actually following a normal distribution, right? So what happens to the next samples? You will have to check it in the same way we just discussed, right? It's going to go ahead and go to normality test, right? And then you will select prototype B, right? And then select Anderson-Darling test, click OK. Again, it is more than 0.05. So we've proven that prototype B is also following a normal distribution. So that condition is also met, right? And the third one which is remaining is prototype C. So I'll just go to basic statistics, stat, basic statistics, normality test, and then I will select prototype C, right? Anderson-Darling test, okay. Again it is 0.9, so it is really normal. So I have satisfied my first condition is obviously it's a continuous data, and the second condition is it normally distributed or not, and that is also taken care, right? So we have proven the second condition, and what's the third condition for us? Our third condition is basically to check the variance, whether all the levels, we have got 3 levels in here, right? Prototype A, prototype B, and prototype C. And what is your Y? Your Y is nautical miles, the flight range, right? So you need to ensure that the variance between prototype A, prototype B, and prototype C are equal. Variance in prototype A, prototype B, and prototype C are equal. So how do you do that? Again, I go back to start, click on start on top, right? And then I go to Anova, test of equal variance, right? And this is the tab what I get, right? So when I open the tab, test of equal variance. So now in test of equal variance, what I'm going to tell, responses are in separate column, because I have got prototype A, prototype B, and prototype C in separate columns, right? So each factor level, each level is in separate. So I select all of those things, click on select, options, confidence is 95%, use the test based on normal distribution, because we have proven that it is all following the normal distribution. So you can click on this, OK, and click OK. Right? So you have got this window popping up, which is the test of equal variance, and you have a p-value again here, right? So what's the null hypothesis for us? All the 3 types are having equal variance, right? So alternate is at least one variance is different from the rest of it. So I have 46% risk in rejecting my null hypothesis. So I will not go ahead and reject my null hypothesis. So I'll accept it. That means all the 3 prototypes are having equal variance, and visually also you can see these are the confidence intervals, right? So all of these things, confidence intervals, are overlapping. That means none of them are statistically different. All the 3 are having equal variance. So that's also proven. So this is, by doing this, we are proving the third condition of Anova. And what did I finally say? Once you meet all the 3 conditions, you go ahead and do the Anova in Minitab. So how do I do that? So again, I'll go to start on top, Anova, one-way Anova, right? This is what you can get to see in your screen. And I will select all factors in different column, right? This is the default. So I will select again, okay. And options, it's obviously at 95%, right? Type of confidence interval, it should be always 2-sided, because when I'm taking 5% risk in a normal distribution, my 5% is getting distributed to both the tails of the normal distribution, 0.25% and 0.25%, right? The reason being that I just want to check the equivalence of means. I'm not here to prove whether one is more than the other or the other one is lesser than the other. No, I just want to see whether they are equal or not. It could be more or it could be different, right? So I select the 2-sided thing, and here I will discuss about this, but just to ensure that you come to your comparisons and select on to keep. I'm going to talk about it, okay? And then storage you will come, right? You will click on I want to store the residuals also, okay? So far so good. And then now we're going to click OK. So you would have got a similar window after doing the analysis, right? So I've got prototype A mean, prototype B mean, and prototype C mean. I see here visually the confidence interval of mean for prototype A is very, very distinctly different from B and C, because I see overlaps here, right? These 2 things are overlapping, but this is quite different and it is not overlapping at all. So that means there is a chance that my prototype A could be significantly different, or the mean could be significantly different from prototype B and prototype C. This is what I get first thing as a visual result. Okay, so now let's look at the statistics of it, right? So I hope you can see my window. Yes. So let's get to see what is the result in the session window talking about, right? Okay, so this is the one-way Anova analysis, right? Null hypothesis, all means are equal, alternate hypothesis at least one is different, and significant levels is at 5%. It's 95% confidence level you are taking, right? Equal variance are assumed. Why I have assumed it? Because we have already proven that, right? In factor information, 3 levels of data: prototype A, prototype B, and prototype C. These are the 3 levels of data in that. Okay, so now this is the most important part of the analysis of variance, right? So factor or model, I just spoke about it. This is nothing but between variation, and error is within variation. Total is total variation. So this is something what you will have to understand. So in Minitab, when you run this, so when you see factor, you should understand this is nothing but between variation, error is within variation, and total is total variation. DF stands for degrees of freedom. How to calculate it? How many factors do I have? How many levels do I have? So to calculate between, I have got 3 levels. So what's the degrees of freedom? 3 minus 1 for me, right? So that becomes 2 degrees of freedom, because I have got 3 factors, right? 3 levels. So 3 minus 1, 2 I can arbitrarily play with, but 1 will remain out of my choice. So that becomes 2 for me. And what is within? So I have already consumed 2 degrees of freedom, right? 2 degrees of freedom here. And what is error? Error is nothing but within variation. So how many total data points do I have? I have got 30 data points, right? And 3 factors have already consumed. I have already estimated for 3 individual means, right? Level A, level B, and level C. So I have to reduce that from my total. So 27 minus the number of factors I've already estimated, that will become 3. 30 minus 3 will become 27 for me. And I add these 2 things together, and that will be total of 29 degrees of freedom, right? Adjusted sum of squares, nothing but sum of squares, right? You would have already calculated the mean, and from that mean you are trying to take the individual differences and square the values. So you will do it for between, and you do it for within, and then you add these 2 things together, you will get 629587, right? Now adjusted mean square is nothing but your variance, right? So all you need to do is 381127 divided by 2, right? This is a means sum of squares divided by degrees of freedom. That gives you the variance. This is nothing but the variance, right? And again, for error, which is nothing but within, I'm going to divide this sum of squares divided by 2 degrees of freedom, 9202. And if I take the ratio of these 2 things, is what I will get the F value, right? F value we discussed, right? And this is the ratio. This is nothing but the ratio between 190563 divided by 9202, F value, right? Now there are 2 ways in which I can prove or conclude this analysis. I can go ahead and open the standard F distribution, right? And I will check the numerator degrees of freedom as 2, denominator degrees of freedom as 27, and corresponding value I will find out from the F distribution table, right? So that will become the F critical value for me, right? So in any case, if the F value is higher than that value, that means my test is significant, and I will have only less than 5% risk in rejecting my null hypothesis. So here, that job is already done by Minitab, and what is the p-value you got here? It is 0%. So there is 0% risk in rejecting my null hypothesis. What's my null hypothesis? All means are equal. So I'm rejecting it. So what is true now? Alternate at least. At least one mean is different, right? So hence, since p-value is less than 0.05, I will go ahead and reject my null hypothesis and accept the alternate hypothesis. At least one mean is different, right? Now you can take decisions in two ways. We've already seen the visuals, right? I'm suspecting what? Here, my mean of prototype A is significantly different from B and C. Visually, I have concluded that. Now, if I have to statistically conclude, right, there is another analysis which I remember when I did the Minitab setting, I clicked on something called as Tukey. So that is Tukey's simultaneous 95% confidence interval, right? So wherever I have a doubt, so when prototype B and prototype A gets compared, right, this is the difference, prototype B minus prototype A, right? I'm getting this difference. Prototype C and prototype A, if the means I'm taking, I'm getting this difference. And prototype C and prototype B, this is the difference what I'm getting. So to make it a little more easier for you to understand, I will take you to the session window, roll down. Okay, so now in this area we've got the means listed, right? And Tukey's pairwise comparison is gonna check the means, and then it is gonna compare it with in pairs, right? How many pairs will be there in this? There will be 3 pairs, right? A compared with B, A compared with C, right? And B compared with C. A compared with B, A compared with C, and B compared with C. So all these 3 combinations we have checked. So we see that, prototype B and prototype C are somewhat similar in nature. They are same, but A is very, very different. So if you want to conclude your analysis of variance, you will say that prototype A is significantly different from prototype B and C. Okay, so you can either visually conclude it, or if you want some statistical evidence to it, you can always come to Tukey's pairwise comparison, click on it and see which are the ones which are equal and which is significantly different from. So B and B, the letter B used, that means these 2 things are similar. So that's the reason why both of them are in B group. But A group is something which is different from B group. So what is in A group? It is prototype A. So this is how you do the Tukey's comparison as well, right? So this is how we conclude the analysis of variance. Now we did discuss about 3 post-model conditions which are very, very important to you, right? So I have already in the storage, I've clicked for storing my residuals. So if I go back to the sheet, I get to see the residuals of all the 3, right? So these are the residuals what I have received. So what I need to do, I'll just go ahead and check 2 things. One is I will go ahead and do the normality test of this, right? So I will check for each of these. Residual 1, what's my normality? Yes, it is normally distributed, it's 0.523, and now residual 2, it's 0.475, it's absolutely fine. It is normally distributed, and I'll check for the third one as well. It's 0.906. So my first post condition is also met. That means it is normally distributed. Now my second condition is that it should be independent with each other. How do I check it? Right? I can easily run a run chart, right? Or I can even run a control chart over it. So for simplicity's sake, I'll just do a time series plot and see whether how my residuals are behaving. Okay. It's random, right? It doesn't follow a pattern. It doesn't really correlate with each other, right? It is all random in nature. So it is random in nature, right? And it's obviously normally distributed, right? So I'm having one more condition to be met, which is that the mean of residuals must contain 0. What do? I just go to basic statistics, display or graphical summary, and I'm going to choose all these three things together. Click OK. So obviously I've got to check minus 51 to 51. So obviously 0 is contained in this, right? So residual 3 is taken care. It's minus 75 to 75. It's 0 is taken care. Because 0, we are saying that 0 must be contained, right? So residual 1 and residual 3 are taken care. Now let's look at residual 2. Minus 76 to 76. So that means 0 is present there as well, right? This range contains 0. So we have already met all the post conditions as well. So that means our Anova is a good model. We can use it, and our predictions or our hypothesis testing are going to be really sound and valid. Okay, so I hope that you have understood how to conduct these Anova or analysis of variance using Minitab, and that's what I wanted to cover in this video. And there is an easy way in which you can do this in Excel as well, right? So I can show you very quickly in terms of how do we get it done, right? I've just opened the Excel. I'm not going to go into the details. These formulas are already available. So this is how we do it. You know, we have got all the information out here, the 10 samples, right? And then X bar is nothing but the mean. I'm going to calculate the average of each level. So I've calculated 4407, average of this and average of this as well. Okay, and then the grand mean is nothing but the total average of all the 30 items. So I've got two things in my hand. One is the X bar, which is but nothing but the mean of individual prototypes, and grand mean is the overall mean of all the three prototypes put together. And the first thing what I need to calculate here is the between variation. So between variation, as you know, that I'm going to check the variation between factor A, factor B and factor C, or level A, level B and level C. How do I do that? It's very simple. You've got this formula available, right? So you are going to first calculate the variance of it, right? You're going to individually take the difference of the X bar and the overall mean or the grand mean, right? And then square it, because it becomes the sum of squares, and then multiply it with 10 because I've got 10 samples here, right? So individually I'm going to calculate the sum of squares of each level, right? And then add all these three things together, and that becomes my sum of square variation for between, right? And what is within? Within is slightly complicated to calculate, so it's always good to calculate total, right? So total is, again, you know, it is very easy to calculate, but it's a lengthy process. But let me show you 2 or 3 things, and then the remaining things are just the follow on of that, right? So first is you got to calculate the total variation, right? So how do you calculate the total variation? You have to individually take every observation and minus it or difference it with the grand mean, square it, that becomes the sum of square, right? And add it. So this will follow, right? Now we will go ahead, take the difference of this value with the grand mean and then square it, plus, and then you will do it with this, everything differenced with the grand mean and squared. So when I take the sum of it, I'll get some value which is equal to 248460.333. So, and I just go ahead and add the total difference, total variation will become the sum of these two things, right? If I take the sum of these two things, it's 629587, which you can see on the screen, and I'll add this. So degrees of freedom we have already seen. Between variation 3 minus 1 2, total within I've already exhausted 3, so I've got 30. So 30 minus 3, 27, and I just need to add these two things. Total difference of freedom becomes 29 for me. The next step was to calculate the variance, right? As I told you, this is the sum of squares. These are nothing but sum of squares, right? So I just need to divide the sum of squares to the degrees of freedom. So I get the individual variance. So again, the same individual variance, right? And if I take the ratio of these two things, I get the F value, right? I just need to take the ratio of these two things. And to get the P value, you just need to remember this formula is equal to F distribution, numerator degrees of freedom, that is which is the X value. Obviously the X value is 20.7, right? That's the value what I want to prove in the compare it in the standard F distribution. And what are the degrees of freedom? My first degrees of freedom, numerator degrees of freedom is 2 and denominator degrees of freedom is 27. So this is going to kick me out the P value. So this is nothing but the P value, right? So P value is obviously lesser than 0.05. So I go ahead and easily reject my null hypothesis and say that at least one mean is different. So this is how you do the Anova manually in an Excel. So even if you don't have an access to a Minitab, you can easily do Anova in an Excel sheet as well. So if you need any clarifications or any more detailing in terms of how to do it manually, please feel free to drop an email to me at info@trainfirm.com. I will individually attend to your queries and try and resolve it as quick as possible. Okay, so have a great day. I hope you enjoyed the video, and if you've got any doubts, please drop us an email. We will try and help you, and if required, we can even get on to a one-on-one WebEx session to clear your doubts. So keep using these tools in your projects, and happy learning to you all. Thank you so much.